Hello everyone, this is the first little video lesson that I'm going to put up for you. So the idea is that it's just a short video with me talking through some information, doing a few examples, and then you guys will do some questions afterwards, kind of similar to what we would do in class. The first thing we're going to look at today is units, prefixes, and scientific notation. So hopefully by the end of this little lesson, you will know what we mean by SI units, and you also know how to use prefixes and scientific notation, and then how to use the correct number of significant figures in calculations. So the first thing we're going to look into is SI units. You've probably come across these before, even if you've not heard of this actual phrase. But the SI unit stands for the Système International de Units, or the International System of Units. And it's basically just the preferred units that we use in science. So, meters, seconds, things like that. Those are the sort of standardized units across the world. The SI system is all based on 5 simple units, which would be meters for distance, seconds for time, Kelvin for temperature, amperes for current, and kilograms for mass. So you can derive, or you can basically make all the other scientific units from these basic 5 units when it comes down to it. It's basically as well, it's kind of the system, the SI units are what we call the metric units. And just looking at the map here, kind of shows that how much of the world is using the SI units, and the majority of it. So the only countries that use imperial are America, Liberia, and Myanmar. And the reason that UK is mixed is because although we are actually a metric country, we still do distances in miles. So all the road signs are in miles, and we tend to talk about people's masses in stones and kilograms, stones and pounds instead of kilograms, which we should actually do, which is why we're mixed. But all building, construction, engineering work uses metric, which is why it's mainly metric. That's just a little bit of background information about the SI units. We'll cover them as we come through the course in more detail, and you'll have a note of all the units that we need for the physical quantities. So that's SI units taken care of. Now we're going to look into what we call scientific notation. You've probably come across this a little bit last year and third year, but quite often we're going to deal with very, very large numbers. So a lot of the frequencies are very, very large, and then we're also dealing with very small numbers. So again, some of the wavelengths for light that we deal with are very, very small numbers. So instead of writing out, 1, 0, 0, 0, 0, loads of zeros, we use what we call scientific notation. And that's just when we multiply a number by a power of 10. So when we talk about power of 10, what we mean is like 10 to the power of 2, that's just 10 squared, is 100. 10 to the power of 3 is 1,000. Okay, so instead of writing out 1,000, we can just write out 10 to the power of 3. When it's not too big, you're not really saving yourself that much time and space. 10 to the power of 3 is only one digit fewer than 1,000, but if we're thinking about 10 to the power of 9, that would be 10 followed by 9 zeros. 3, 7, 8, 9, 3, 3. So, this is much easier to write than this. Okay, so for example, so the way that we talk about by multiplying a number, we could say that 4,000 is equal to 4 times 1,000. We know that 1,000 is 10 to the power of 3. So we can also write that as 4 times 10 to the power of 3. Okay, so these two, 4,000 and 4 times 10 to the power of 3, are equivalent. That's the same number. Okay, so that's what we mean when we talk about multiplying a number by a power of 10. So if the power of 10 is positive, it's going to be a big number. And the decimal point would jump to the right. So what we mean by that is, so let's say we've got 6.2 times 10 to the power of 6. To write this out in its full form, we would write 6. So the decimal point is going to go here, and it's going to jump to the right the number of times that we've got the power. So it would go 1, 2, 3, 4, 5, 6. Your decimal point is going to be here. So I want a 0, 1, 2, 3, 4, 5. Okay, so 6.2 times 10 to the 6 is 6,200,000. Okay, so that's what we mean by sort of jumping to the right. You take your decimal point and you jump it the same number as the power. Okay, if it's a positive number, we go to the right. If the number is negative, that means that the number is going to be much smaller, okay, than the number given. And the decimal point jumps over to the left. So we'll use the same initial number, 6.2. So 6.2. But this time, let's say it was 10 to the minus 6. Okay, so we'd start off the same format. We'll go 6 and the 2. Our decimal point was here, and we're going to the left this time. So we'd go 1, 2, 3, 4, 5, 6. And our decimal point is going to be here. So we're going to have to put 0 in front of it. And then we've got 1, 2, 3, 4, 5. So 6.2 times 10 to the minus 6, excuse me, is equal to 0.0000062. Okay? So, just to recap that, if our power of 10 is positive, okay, our decimal point is moving off to the right, the same number as the power. If the power of 10 is negative, our decimal point is moving to the left. Just make that clear, it's moving to the left the same number of times as the power. Okay, so positive to the right, negative to the left. Okay. It can be expressed in different ways. So far we've had sort of a 10 to the power of a number, say it was 4. Okay, so if you write a small number to the top right hand side of a number, that means it's to the power of it. Sometimes in sort of Word documents or in certain formats where you can't get what we call the superscript number, we do this sign chevron here, which means to the power. So if you see sort of 10, that sign 2 is the same as 10 squared. In Excel and calculators, it can use a big E or a small e. So 6e plus 5 would be the same as 6 times 10 to the power of 5, or 6 times 10 to the power of 5, something like that. Okay, so that's just different ways to write the same thing. Okay, this one can is what if you've got a calculator that uses this format, this would be the button to use instead of some calculators that have a times 10 to the x button that you can use. Okay. Again, we like to make life even easier for ourselves. So instead of writing out, say, times 10 to the power of 9, you can just write a capital G for giga. Okay, these are the prefixes that you'll come across in National 5 physics. So giga is times 10 to the 9, mega is times 10 to the 6, kilo is times 10 to the power of 3, milli is times 10 to the minus 3. So that would be multiplying your number by 0.001 or dividing by 1,000. Okay. Micro, which is this Greek symbol here, mu. Okay, so it's a U with a little extra leg on it. It's 10 to the minus 6, so that's dividing by a million. And nano is 10 to the minus 9, which is dividing by, what's that, a billion? Yeah, dividing by a billion. Okay. Again, you'll have come across these before. If when we get back, we'll have a copy of this in your jotters for your own reference all the time. So that's our prefixes covered. And now we're going to look at significant figures. So the significant figure is just the number of what we call meaningful digits in a measured or calculated quantity. Okay, so just going to go over. There are 5 rules essentially about what constitutes a significant figure. I'm just going to go through them now. So the first rule is that any digit that is non-zero is significant. So, for example, 1,289, all the digits are non-zero. That's got 4 significant figures. Okay, 6.5348. Again, all the digits are non-zero, so they're all significant. This has 1, 2, 3, 4, 5 significant figures. So any digit that is not 0 is significant. Okay. Second rule is that zeros between non-zero digits count. So 1,001, the zeros are between 2 non-zero digits, and so that has 1, 2, 3, 4 significant figures. Okay. 6.05, again, 0 between the 2 non-zero digits, 3 significant figures. Okay, so these are our first 2 rules. Any non-zero digit is significant, and zeros between non-zero digits are significant. The third rule is that zeros to the left of the first non-zero digit are not significant. So if you had the 0.8, this is to the left of your first non-zero digit, doesn't count, that's just got 1 significant figure. Okay, 0.384, again, 0 to the left, not significant, 3 significant figures. Okay, so zeros to the left of the first non-zero digit are not significant. The fourth rule, for numbers with a decimal point, zeros to the right of a non-zero digit are significant. Okay, so for example, 0.480 has a 0 to the right of this 8 here, which is non-zero, and so that is a significant number, figure, sorry, and so that would have 3 significant figures. 0.090, okay, a little bit more confusing, okay, quite a lot going on here. This number here is not going to be significant. It's to the left of the first non-zero digit. However, this number here is significant, so we're going to have 2 significant figures. Okay, so zeros to the right of a non-zero digit are significant. 0 to the left of the first non-zero digit are not significant. The final rule, so if numbers don't have a decimal point, trailing zeros are not significant. What do I mean by that? Trailing zeros are just numbers to the right. Okay, so trailing zeros, we've got 3 trailing zeros here. One, so that would be one significant figure. Okay. And then let's say we had, I don't know, 101,000. Okay, this would have 3 significant figures. Okay, this becomes a little bit more clearer if we write this number in scientific notation. Okay, because we could rewrite this as 1, 2, 3, 4. So if we wrote it as 101 times 10 to the power of 3, you can see there that that has 3 significant figures. Okay, so using your powers of 10 can help you work out how many significant figures. Oh, excuse me. Sorry. How many significant figures your number has. Okay. When you're doing calculations with different amounts of numbers, your final answer should contain the same number of significant figures as the value with the fewest number of significant figures in the question. So, just as an example, if we were to calculate the wavelength of a radio signal of frequency 2100 megahertz. Don't worry if you don't know the formula, we'll cover that when we get there, but what we need to know is that the speed, we get that from the data book, is 3.0 times 10 to the 8 meters per second. Our frequency, if we get this from here, is 2100 megahertz. So mega was times 10 to the 6 hertz. Okay, our wavelength is just the speed divided by the frequency. So it's P divided by F, which is 3.0 times 10 to the 8 divided by 100 times 10 to the 6, which is, where's my calculator gone? 3 times 10 to the 8 to 100 times 10 to the 6. So my calculator tells me that this is 0.1428571429. Okay, now this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant figures. We are kind of already intuitively, that's far too many. If we look back to the question, this has 2 significant figures. This also has 2 significant figures. So we need to put our answer to 2 significant figures. So 0 is not significant. 1, 4, there's our 2 significant figures here, 1, 4. The number after the 4 is a 2, so we just round that down to 0.14 meters. Okay, so there's our answer rounded to 2 significant figures. So it can help if you're writing down information at the top, write down the numbers. Okay, until you get used to it, it might be worth just writing down how many significant figures each of the values has. Okay, hopefully we should be aware of this, but when we're rounding, you check the value of the digit immediately after the last significant figure. So for our one, that was 0.14. if the digit is from 0 to 4, so for that example, we had 0.142. 2 was between 0 and 4, so we round down 0.14. Let's say, for example, it was 0.148. This would be rounded to 0.15. Okay. Yeah, it's fairly straightforward rounding. You just got to check the digit after the one that you're interested in, and then you round that up or down. What we need to be aware of, though, is if your answer is something like 0.999 and you wanted to round that to two significant figures, okay, here's our last significant figure is 9. We're going to round up, so that becomes a 10. So then we'd have to make this to a 10. So that would actually be 0.10. It is important to remember that this last 0, because it is significant. If you were to just say it was 0.1, that's just one significant figure. Okay, but we need 2 for our answers, which is why we need to include that extra 0 there. Right, I've put up a Google form with just a few questions, there's not too many, on scientific notation, prefixes, and some significant figures. Have a go at it and see how you get on. If you've got any questions or you'd like a few more problems, let me know and I can post them too. Oh, sorry. I'll also post this year, there'll be a little bit, I'll post up this PowerPoint with the examples included, so you can have a look at it at your own leisure. And there's a link here to a scientific notation website with a few questions for you to try if you want some more. And there's also a little video there that you can watch as well. Okay, again, if you've got any questions, just drop me an email and I'll do my best to answer it. Okay.